You spend hours building a precise, mathematically aligned UI component. It looks perfect in your development environment, but the moment you drop it into a different section of your live application, the layout breaks, the text overflows, and the structural integrity shatters. For years, developers have tried to prevent this by relying heavily on traditional responsive design, which is almost entirely dependent on CSS media queries. The mechanical logic of a media query is straightforward. It forces an element to adapt its layout based entirely on the global dimensions of the user's browser window. If the screen is wider than 1,000 pixels, the code tells the layout to expand. This diagram illustrates a critical failure point known as the sidebar problem. Here, we have a wide browser viewport, but the UI card placed inside the narrow sidebar column is overflowing, with its text and buttons bleeding out of their container. A wide browser window does not guarantee wide layout space for the elements inside it. This failure occurs because the component's code is mathematically coupled to the global viewport. It looks at the massive browser window, assumes it has plenty of room, and renders a wide layout, remaining completely blind to the narrow physical constraints of the sidebar it actually lives in. Because components are blind to their immediate surroundings, developers are forced to write redundant, highly specific code overrides for every possible nested context. You end up writing one rule for the card on the main page, another for the card in the sidebar, and another for the card in a footer. Addressing this specific friction, the gap between the size of the browser window and the actual local environment of the UI component, is the core focus of the modern web strategies we develop and analyze at Royal Research. To build robust, modular interfaces, we have to stop designing around rigid breakpoints. The solution lies in a three-pillar architectural system: fluid layouts, progressive enhancement, and container queries. Designing UI components based on global viewport state breaks component reusability. It creates a brittle architecture that requires constant manual intervention to maintain. To fix this, we have to rethink the basic geometry of web elements. We need a system where elements calculate their own scale automatically without needing a developer to manually assign a new pixel value for every possible device. This 2D line graph maps viewport width on the x-axis against element width on the y-axis. The rigid staircase pattern plotted here represents the mathematical behavior of traditional media queries. It operates as a step function, snapping an element into a new fixed size only when the screen hits a highly specific pixel threshold. Relying on this rigid step function causes unnatural visual jumps as the user resizes their screen. It also requires developers to constantly test the awkward, unpredictable spatial gaps that exist between the defined breakpoints. Fluid layouts offer a mathematical alternative. Instead of jumping between fixed states, the layout adapts along a smooth, continuous linear progression. This continuous adaptation is achieved by abandoning absolute pixel values in favor of relative units, like percentages. When you set a container to 80%, it will claim exactly that fraction of its parent element, calculating its own size dynamically on any screen. CSS also provides viewport units, VW for width and VH for height. These calculate geometry based directly on fractions of the available screen space. 1 VW is exactly 1% of the viewport's width, allowing elements to scale in direct proportion to the device. Letting the browser handle the math introduces a new risk. Without limits, an infinitely scaling fluid element will stretch too far on an ultra-wide monitor, or shrink into total illegibility on a tiny mobile display. To control this, CSS uses min-width and max-width properties. These act as hard safety boundaries, capping the continuous fluid function at defined limits to guarantee the text remains readable and the buttons remain clickable. By establishing these boundaries, fluid layouts replace hundreds of lines of discrete, error-prone breakpoint code with a single, continuous mathematical equation. While fluid math makes layouts adaptable, it doesn't solve the problem of how a browser actually handles the code. Every line of CSS we write has a performance cost, especially on mobile hardware with limited processing power. This brings us to the logic of progressive enhancement, widely recognized in development circles as a mobile-first strategy. This split-screen visualization of a CSS rendering engine shows the flaw in desktop-first architecture. On the left, the browser is forced to download and process a massive block of complex layout rules. Then, media queries engage, aggressively crossing out and overwriting that same code to force the heavy layout onto a small screen. On low-power mobile devices, this is highly inefficient. The processor wastes compute cycles and bandwidth interpreting heavy, complex rules that the user will never actually see, only to spend more compute tearing them down. The optimized approach is on the right. Mobile-first architecture establishes the simplest, lowest complexity UI as the absolute base state of the CSS tree. A lightweight block of CSS loads instantly. Then, as the system detects more screen space, it cleanly adds instructions to expand the grid. In this paradigm, media queries serve an entirely different function. They are strictly additive, triggering only to build upon the foundation, never forcing the browser to subtract or overwrite existing instructions. This code architecture forces a strict content strategy. Starting with the smallest possible footprint means you have to prioritize the most essential information, stripping away distractions before the first line of CSS is even written. Progressive enhancement operates as an architectural safeguard. It protects device performance by ensuring that complexity directly matches the hardware constraints of the user's machine. Fluid scaling handles the geometry, and optimized rendering handles the processor. But neither of these fixes the sidebar problem. The UI component is still checking the global viewport to decide how it should act. To sever that final dependency, modern CSS introduces container queries, written as the @container rule. Returning to the wireframe from earlier, watch what happens when we apply a container query. A glowing bounding box activates around the sidebar itself. This boundary visually severs the card's connection to the wider browser window. Recognizing its new constraints, the card instantly snaps into a vertically stacked, highly functional layout. The underlying logic is reversed. Container queries allow the UI component to interrogate the exact physical dimensions of its immediate parent, rather than looking out at the distant global viewport. This creates true component-level responsiveness. If we copy that exact same card and paste it into a wide main content area, it reads the new, larger parent boundary and instantly expands into a horizontal layout, without a single line of code being changed. You are no longer writing context-specific overrides. You write the component once, define its internal layout rules, and it will autonomously adapt to wherever you place it in the application. Because container queries are a relatively recent native addition to CSS, they do sit on an emerging adoption curve and may not be universally supported on older browser versions. To safely implement them in production, developers utilize polyfills or establish strategic fallback styles using traditional media queries, ensuring functionality for all users. Container queries change how UI elements function. At Royal Research, we've seen how, instead of remaining passive dependents tied to the global screen size, they operate as autonomous, context-aware architectural modules. None of these three techniques are designed to operate in a vacuum. Their exact utility scales when they are engineered together into a single cohesive framework. This 3D structural model breaks down how a modern interface is built. We start with a solid base layer representing our mobile-first logic. Then we stretch a flexible geometric layer over it to establish fluid relative units. Finally, modular component blocks drop onto the grid, representing isolated container queries. The first layer, the mobile-first logic, protects the browser. It handles the core render path and ensures high-speed computational performance across all devices. The second layer, fluid layout geometry, handles the spatial gaps. It provides a continuous mathematical scale to accommodate every unpredictable screen size on the market. The third layer utilizes container queries to enforce strict, localized boundaries. This guarantees the structural integrity of every individual module, regardless of where it is placed. At Royal Research, we find that integrating these three pillars creates a more predictable development workflow and a more resilient user interface. By prioritizing local, fluid contexts over global screen assumptions, developers can build interfaces that adapt accurately to any screen, regardless of its dimensions.